Okay, good evening, everyone, and welcome to the beginning of our machine learning class. So, of course, this is the first day of our course on the KodeCamp 5X, which is our AI cohort of KodeCamp, and I welcome everyone. My name is Aniebiet Udo, and I'll be taking everyone on this journey through machine learning. And just to clarify, for those who are not yet very clear on this, the machine learning core track is going to focus on training you to become someone who designs, who builds, and who trains models. We will really be focusing on more modern techniques, especially neural networks in particular. But in spite of that, we will still be touching on a lot of the older techniques that have been used in the past, what I call classical machine learning. And we will learn about all of those. So I'm just going to kick this off. So this is what we expect to achieve at the end of this week. This is the objective for this week, right? We are in week 1. And in week 1, we are going to look at introduction to machine learning. We're going to look at overview concepts and definitions. Then we'll talk about differences between AI, machine learning, deep learning, reinforcement learning. And then after that, we'll look at key milestones in the history of machine learning, from perceptrons to deep learning to large language models. And then understanding typical machine learning lifecycle, how you prep your data, train, and then do deployment. Then we'll also look at a few of the modern machine learning frameworks that we currently are using. These are the ones that are most popular around the world. And then we'll also take a look at how to set up your machine learning environment using Jupyter Notebook, Google Colab, and a bunch of other tools. We'll also do an introduction to data processing. Now, for the benefit of everyone, let me just, I forgot to mention that the full curriculum is in the KodeCamp LMS. So if you haven't already LMS reached into the entire track, let me just take a few moments just to take us through that. So I'm going to open it up in the LMS, and then I'll show us how that looks like. So we're going to start off just by looking at the we're going to start off by looking at machine learning introduction. Then we're going to look at how we prepare our systems, our computers, that to be able to handle machine learning tasks. We're going to look at the tools, and then we are going to look at the different approaches that we use in machine learning. So let me just go through, give me a minute, let me bring up the screen so that you can look at the curriculum. Okay, so we're going to run this course for a cumulative of 3 months, and then in the fourth month, we are going to have a capstone project, right? So 12 weeks or about 13 weeks, and then we'll do the capstone project. So in the first week, we are looking at introduction. That is where we currently are, introduction to machine learning. Then you can see the subtopics that we have there, which is what I've already mentioned. Then in the second week, we are going to we'll start looking at basics of machine learning, the basic principles, the basic techniques, what we call regression and classification, which are the two main approaches that we use for learning and for prediction, right? And then after that, we will look at week 3 in the third week. So for your information, this regression classification, there's a lot of maths in it. So I hope everyone is prepared for that, because you definitely need to wrap your brain around a bit of mathematics in order to be able to grasp some of these. I'm actually going to go into the weeds in all of these, especially mathematics aspects, so that everyone has a good grasp for it. So in week 3, we are going to look at what I call the classical machine learning approaches or algorithms. We're going to look at classification and regression using decision trees, random forests, gradient boosting. There are libraries and tools for doing that, but we'll learn the basics and then we'll apply. Then we'll look at support vector machines, SVMs, k-nearest neighbors, and a bunch of other approaches as well. Then we'll look at clustering. Clustering is unsupervised learning. So we have k-means clustering, dbScan, and then dimensionality reduction using the PCA approach. So this would be kind of introduction and quickly touching the classical machine learning. Then we'll do a bit of unsupervised and self-supervised learning. So we'll talk about feature engineering and preparing data. We'll talk about things like normalization, encoding, feature selection. And then we'll start talking a bit about data, how you prepare data and how you clean and get all your data ready, including augmentation for the training pipeline. And then we look at self-supervised learning and then contrastive representation learning. So all of that we'll cover in week 4. Then week 5, we go straight into neural networks. The world of AI today has been dominated by neural networks simply because of the easiness to build and to train, right? But also their capacity and their capability. So we'll go into the fundamentals, right from what we call a neuron, perceptron, and then we'll look at things like activation weights, layers. Then we will do a bit of the maths around neural networks, which is how do neural networks learn? So we have what we call forward propagation and backward propagation, and how you can backpropagate. Then we'll look at how you can implement a simple neural network using PyTorch. Of course, before now, we would have done some introduction into PyTorch, so you would have had some knowledge of PyTorch. PyTorch is a framework that we typically use for training neural networks, or basically for machine learning generally. Then we'll do what we call a feed-forward network with PyTorch. That's in the 5th week. Then in the 6th week, we start looking at training. So training is the way you basically apply the knowledge in data into a model. So we'll look at gradient descent, stochastic gradient descent, and other types of gradient descent, and other optimization algorithms, including Adam extended, and then different learning schedulers for learning rate adjustments. Then we'll talk about regularization. What's regularization and why do we do regularization? Dropout, weight decay, loss curves. We look at things like overfitting and how you can detect that. We'll define all of these concepts. Then what we call loss surface analysis and overfitting detection. In the 7th week, we go into specific architectures of neural networks. So we'll start with the CNN, which is a convolutional neural network that was designed for handling images and other kinds of data that are what they call data that are space invariant, kind of. So we'll look at convolution. What is convolution and why is it so useful? Why is it, so powerful? And then we go into more modern kinds of CNNs, residual networks, efficient networks, and so on, different architectures. After that, we'll go into sequence models in week 8. So sequence models are models that are able to retain historical information. They basically can remember things that happened, in the immediate past, or data that you give to them in the immediate past, and they use that as part of the learning process. So we'll look at the classical sequence models, the recurrent neural networks, and all the different variants of recurrent neural networks. Then we'll look at LSTM, long short-term memory, and GRUs. And then we'll look at what we call sequence-to-sequence models. Then in week 9, we go into attention and transformers. So this is where the big revolution in neural networks happened, when the attention mechanism was discovered and used at scale. So we'll learn about the concept of attention. We'll also understand why it's so powerful. It's basically some mathematical operations that we call scale dot matrix. So for me, what's more interesting is how are these things so powerful, right? We'll look at things like positional encoding, transformer architectures, different types, encoders, decoders, and what we call multi-head attention. And then modern improvements to attention mechanisms. Then in week 10, we'll go to LLMs. So we have been hearing all these LLMs, large language models, the likes of GPT that's used for ChatGPT, and so on. So we are going to study them. We're going to look at their architectures to understand where they came from and why they are so powerful. And because they are large language model, they are really large. You really cannot train an LLM by yourself with unless you have very powerful compute. So we are going to look more at how they are trained from a theoretical standpoint, maybe look at the code, maybe try to do it a bit, maybe look at some small, tiny LLM models. But we'll really focus more on fine-tuning existing models. And there are a lot of open source models out there. So we'll see how we can do that. Then what we call pre-training. So the P in GPT means pre-trained. G means generative. And each of those 3 words mean something. The T means transformer. So basically a GPT, which is the basic architecture of all LLMs. It's a generative neural network that is pre-trained, and it is a transformer. Then we'll look at tokenization, embeddings, masking, and then how you can tune prompts and instructions. Then we'll talk about GANs. GANs are generative adversarial models. So we'll talk about those. Before we had GPTs, we had GANs, and GANs were also very amazing technology. We'll also understand why. Then week 12, we'll learn what we call reinforcement learning. So all this while, we basically will be using what we call supervised learning to train models. But there is something we call unsupervised, and then we have reinforcement learning. Reinforcement learning is different from supervised and unsupervised in the sense that you are not really giving the model training targets, but you are giving it a reward and telling it when it does something right, you give it a positive reward. When it does something wrong, you give it a negative reward, and it learns from there. So look at that's a different class of problem. So after having all this will have given us enough knowledge to apply. So we'll go into application in the capstone project. And there are different projects that we will go through. So that is a summary of the entire course, which we'll be taking in the next couple of months. It will be very interesting. So let's just dive into today's lesson. Today, I'm not going to do a lot of mathematics, and I'm not going to do a lot of programming either. So today is going to be more about talking about AI, machine learning, so that everyone understands. Remember, I assume that everyone in this class basically doesn't have that much knowledge about AI. I'm not going to assume that people already know all of these things. So it will help everyone to kind of get to the same point, even though we're not all starting at the same point, but at least we can all get to the same point. So let's get into it. So what is artificial intelligence? I remember I posted this on our channel and I asked people to tell me what their own idea, what they think AI is, and what's the difference between AI and machine learning, for example, or anything else, right? So I got a lot of really interesting answers, and I think a lot of people, most people had it correct, one way or the other. The only thing is that I want to be very precise. So AI means artificial intelligence. Now, artificial intelligence is used in two different ways or to have two different meanings in the world today, right? So there's artificial intelligence, which is a field of study. And then there is artificial intelligence, which is the product or the thing that has been created from, the field of study. So when you hear of artificial intelligence now, sometimes you can Google it and you're going to see it is something that exhibits human intelligence, right? So that's the second meaning, which is the product of what we are learning. But when you say artificial intelligence, the primary meaning is it is a field of study in computer science, and it's focused on creating machines or making machines. And when we say machines, really the software, right? Not the hardware, because you cannot really program hardware. Even though these days there are people who are talking about things like that, but for now, you want to build software that can exhibit human intelligence. That's a key requirement. It can exhibit or it can appear to be intelligent. So what it means is it may not necessarily be intelligent, but by its behavior or by its response to problems, which are commonly known to be only solvable by humans or using human intelligence, they are able to solve it. So they demonstrate intelligence, but they are not natural. So because they're not natural, they are artificial. That's a simple definition of artificial intelligence, right? So the field that studies this kind of techniques or methods of creating machines or building software, that's what AI is. It's artificial intelligence. So you can now see those two meanings there, the field itself and the things themselves that exhibit artificial intelligence. So we're going to look at a bit of history. It was founded as an academic discipline in 1956. So that's just to tell you that AI has been around for a long time. In fact, there are some places, I'll give you a bunch of Wikipedia references later on, which if you go check it out, you will see that some of them even trace AI all the way back to the 19th century, 18 something, and all of that. But that's not really when AI started, but rather the foundations of the things that led to AI, including electronics, including computing, and all of that. So now the interesting thing with AI is that it went through multiple cycles of optimism and disappointment throughout history. We are going to look at that when we look at the timelines. So I'm just telling everyone here, you're not the first set of people or the first generation that was so excited about AI. AI would conquer the world, AI would change everything. In 1956, or shortly after it was founded in the 60s, people were already talking about in 20 years' time, AI will do everything that a human being can do. And people were betting money on it and all of that. So it's not really new, right? But it's always that kind of cycle. There's a lot of optimism about what AI can achieve. And then a lot of people invest a lot of money and time and effort. And then after some time, the expectations get disappointed. And then people begin to withdraw, right? And then you have what we call an AI winter, which is like, oh, nobody's interested in it again. Nobody's funding it. Nobody's spending money on it. Nobody's investing in it, right? So you have cycles of that, and we're going to look at some of those cycles. Then, yeah, so the traditional goals of AI research include learning. So you want an AI to be able to learn. Reasoning, you want an AI to be able to exhibit reasoning, right? Knowledge representation. So we want to be able to represent knowledge in a way or form that can be manipulated, right? Because you need to be able to manipulate knowledge in order to exhibit intelligence. If you cannot manipulate knowledge, then you cannot exhibit intelligence. And this is how the early AI researchers and experts kind of, viewed AI as something that they have to be able to encapsulate or capture knowledge in a form that you can manipulate it with code, you know. So we'll talk about that also. Then planning, natural language processing. So this is another key element of AI. You should be able to understand human language. You don't need to have some kind of special code for AI to be able to understand you, right? Then perception, which is the ability to see and perceive and differentiate visually the things that are happening around it, right? And that's why we talk about computer vision, because computer vision is an area of AI that just focuses on perception, and then support for robotics. Of course, the perception is one of the key elements, what we call computer vision or robot vision. Now, over time, the AI researchers, from this early 50s or late 50s, and going forward, they have come up with so many different approaches in order to simulate or emulate or, exhibit human intelligence. In fact, this whole cycle of optimism and disappointment, AI winters, have led to so many different branches of AI. That's why if you look at AI, you'll see that there are so many different branches, there are so many different techniques, and so many different ways. In fact, some of you may have been doing stuff that you didn't know was AI, and I'm going to show you, right? We're actually writing code. I don't know that some of the code you're writing is actually AI, but people feel that AI has to, well, okay, it has to exhibit intelligence, right? But sometimes you feel that it has to be something very big and fancy, something very special before you can call it AI. But for real, some people in this class may already have written some AI on their own. And I'm not talking about training neural networks or anything like that. So a wide range of different techniques were adopted, were devised, including search algorithms, right? Mathematical optimization approaches, formal logic, and applying this formal logic. Then, of course, the killer of them are artificial neural networks. By the way, when neural networks started, yeah, we used to call them artificial neural networks, ANNs, right? But these days, nobody bothers to call them artificial anymore. They're just neural networks, right? And when they started, the ANNs were very weak. In fact, they were the worst method of implementing AI, right? And a lot of people left it, but I'll talk about why that was the case. Well, as it is today, we can see that neural networks have basically won the race in terms of what's the best method for you to implement AI, right? Then we also had methods that were based on statistics, basically analyzing data statistically. And so many people came up with such methods. Operations research, economics. So one of the key things you find with AI is that the human beings, in trying to figure out, how best to implement neural networks, or sorry, not neural networks, AI, they looked at things around us. They looked at the human psychology. They looked at human physiology, linguistics, language structures. They looked at philosophy. How do people think? They looked at neuroscience. Neuroscience is the study of how the brain operates, right? So they even went to look at the brain. For your information, this thing we call a neural network, which we'll talk about later on, is based on the structure of the human brain. It's based on the structure of the human brain. That's why it's called neural network. The human brain, for those who know a little bit about, medical field, neuroscience, the human brain is made up of cells. Those cells are called neurons. Those neurons exhibit some special properties, which when you now combine them in large number, those special properties can result to a trainable intelligence, right? So it's a very interesting topic, and you'll be asking yourself, how can intelligence just come out of this? But I'll break it down for everyone. So many other fields, and in picking up from these various fields, we actually came up with very interesting ways to simulate human intelligence and to get this AI. So on the right here, you see some of the tasks that you would use to define an intelligence. It's more or less what I have said, and you see another slide that talks about this, right? Understanding language, being able to speak natural language. That's what we call natural language processing, NLP. So when you hear NLP, natural language processing, it basically means the ability for you to understand and speak human language without any specific code. So far before NLP became very, very, very advanced, you would have to always encode whatever you want to say. That's why we have programming languages now. Programming languages are basically, a small subset of encoded language that helps human beings to communicate to computers or communicate with computers. Okay, then recognizing patterns is another thing. You want an intelligence. Look at a human face, and this is James's face, this is Mary's face. Look at different faces with small differences. You know whose face is who. Or look at objects and know, okay, this is an apple, this is an orange, right? So that's the second thing that we use to define or establish intelligence. Learning from data. So learning, basically, being trainable. So I didn't know anything yesterday, but today I know some more. Or I didn't know this yesterday, but I know today. I didn't know how to play chess yesterday, but I learned a few moves today. Making decisions is what we call planning. There's something called planning problems. So you have to sit and think and plan, right? Okay, that's the last one. And look ahead. Then making decisions is making choices where you are presented with them. So those are what we call the core goals of artificial intelligence. So an AI should have certain capabilities, and I think I've spoken about them already. So the first one is reasoning and problem solving. So it should be able to make a logical deduction or choose between different options or actions based on outcomes that it expects to have or not have, right? So it needs to be able to reason and then make a choice based on that reasoning. So in some situations, you will see that this reasoning is implemented using what we call search algorithms, right? A very clear example of reasoning and problem solving is chess. Interestingly, I'm also part of those that contributes to a chess engine, the second best chess engine in the world, Lila Chess Zero. Of course, the best chess engine in the world is Stockfish. Both are AI, right? But some of us may have heard of 1992, Garry Kasparov versus Deep Blue. That was like the biggest, maybe some people were not born by then anyway, but that was like the biggest AI event, at that point in time, right? So, what basically happened was before that point in time, it was known, chess is a very complex game for those of us who have actually tried to play it or learn how to play it. It is not an easy game. There's what we call draft or trots or checkers. That one is much easier, right? But chess is a really complex game. So one of the key holy grails of AI in those days was an AI that can play chess up to human level and maybe even, compete with a human or defeat a human, right? So there are different ways. We'll talk about that also. I'll talk about that a bit later on, but different ways. But one of the approaches to do this was what we call brute forcing. So you take a chess position, you calculate all the moves in that position, you calculate all the resultant positions from all those moves. You now go into the next level, so what we call the next depth, and you look at each position that results, all the possible positions that result from the first position, right? Which is the opponent's position. And then you now flip sides to the opponent's side. And then you calculate for each position, you calculate all the possible moves. You calculate all the positions that can, come out from those possible moves. And then you keep going down like that. So you have what we call a tree structure from programming standpoint. That is called a tree, right? So this tree, you can explore it to any depth. And if you explore it to any depth, it has exponential, it blows up exponentially. So you can do a simple mathematics about it that if, let's say, in each position, you have an average of 20 moves that you can make, or let's say an average of 10 moves you can make in each position. That means that for each of those 10 moves, there will be 10 resulting positions. And the 10 resulting positions will have another 10 moves. So that's 10 times 10, right? That's 10 raised to the power 2. Depth 2 is 10 raised to the power 2. Depth 3 is 10 raised to the power 3. Depth 4 is 10 raised to the power 4, right? So it explodes like that. So by the time you have played up to, you want to think ahead, maybe 10 moves. You are talking about 10 raised to the power 10 possible variations, right? So you think about that, right? Now, the interesting thing, in some positions, you have even more moves like that. So they use what we call tree search algorithm. Maybe we'll talk about some of that. So that's one of the ways for you to get to the end of the game and say, okay, well, this position, is it a winning position or not? Then when you get to that position and then you see it's winning, you do what we call back propagation, back propagates the outcome all the way back. And that is what is used to distinguish which move should be better and which move should be, worse. They have different algorithms. The most common one that they use today is what they call minimax algorithm. And then there's even what they call A/B pruning, which is alpha-beta pruning of the minimax algorithm, right? So for those of us who have studied algorithms. So that was just one way. And it is still AI. It is still intelligent because, yes, after some years of mastering that process and coming up with faster CPUs, faster chips that were so fast that they could be doing. If you go check out Deep Blue was doing, I think it was how many? Say 10 billion positions per second, right? Yeah, 11.3 billion floating point operations, right? So corresponding to about 200 million chess positions per second. That's what we call 200 mega nodes per second, right? That is Deep Blue. That was the chess engine that beats Garry Kasparov, the world champion, in 1992 or thereabouts, right? Now, by comparison, Stockfish, which is the world's fastest, well, not the fastest chess engine, but the world's best chess engine right now, does 1 million times faster than Deep Blue, right? 200 million. Now, Stockfish does closer to maybe up to 100, billion chess positions per second. So anyway, we'll talk about that. So reasoning and problem solving is one of the things that makes an AI, right? But the interesting thing is that there are different ways you can implement it. But the most important thing is for you to be able to look ahead to see what the outcome is. And then from the outcome, you come back to, is what we call systems thinking. Some people call it systems thinking. If you play chess, you see that you actually think like 4 moves ahead. 5 moves ahead, maybe 10. If you're really very good at chess, you can even go up to 10 moves ahead. But most human beings can only stop. Like me, I stop at 3 moves. After 3 moves, everything falls apart. So I cannot even reason beyond that, right? So that's one. Then the second one is knowledge representation, which is a problem that came up from the need for us to, or for AI researchers to, how do we represent this knowledge? When you say boy, girl, cow, goat, or stockfish, somebody is asking what is stockfish. It's not because we call it stockfish. It's an interesting story. So, but all of these concepts, how do you represent it? How do you put it down? It's not just about representing the words, right? But the relationships between the words. It was a big problem. Like if I represent man and woman, what's the relationship? Mathematical relationship or programmatic relationship between those. If I represent man and woman, then what of the equivalent, for boy and girl, right? So being able to represent knowledge in such a way that the relationships between those entities that you are representing become apparent right in the relationship that you have created or in the representations. That was a big problem. And a lot of people came up with different ways of doing that, right? So how do you encode a fact? Like saying something like, this house is white. How do I represent that information? If I want to, because for you to be able to manipulate, like I said, to exhibit intelligence, you have to be able to manipulate knowledge. But for you to be able to manipulate knowledge, you have to be able to represent it, from the standpoint of a computer program, or even as a human being. Each and every one of us, we have an internal representation of every piece of knowledge that we have. So, but how can I put that down into software? That was a problem. So knowledge representation, how can you encode facts like the sun rises in the morning or the sky is blue, objects, relationship between these things, time, causality, cause and effect. If this thing happens, then it will cause the other thing. Defaults, common sense. How can you encode all of these things into a knowledge base? And ontology. Ontology is basically a study of, properties of things, right? So that when you now throw this thing at software, it will be able to make logical sense of them, or you can combine them and it will still give you some kind of logical feeling about it. So that was a problem. And a lot of people came up with different ways of doing that. Then planning and decision making. So that's another, intelligence problem. Like, what action should I choose? What should I do if I'm faced with 5 different options? Go left, go right, go up, go down. Which one is the optimal choice I should make, right? So that's still another problem for intelligence, for AI, right? They have to be able to choose actions to maximize what we call the utility, the expected utility. Utility is a word that means basically the value of the outcome, right? Or ultimately, in fact, think of it as usefulness. That's what utility means. Like, this thing I'm going to do, what will be the outcome of it? How do I maximize the outcome? What is my expected, value for that outcome? So, and decision problems are always fraught with uncertainty. That's why it's difficult. If you knew the exact choice to make, it's not a problem. You just make that one. But you have several choices to make as an AI. I don't know which one to make, right? So you have uncertainties, and so you have to manage all of that. So there's a field we call game theory. Game theory is a very interesting field. I think everyone should kind of look into it, right? But you learn a lot. You see a lot of machine learning and AI was developed, in the context of game theory. That's where chess comes in. Chess is one of the games, right? And there are a bunch of other games. In fact, in the world today, you hear of things like Alpha Zero, right? By the way, Lila Chess Zero came from Alpha Zero. You hear of AlphaGo. You hear of Alpha Star. These are, models that were built by Google DeepMind. DeepMind is basically the AI part of Google. That's where their brains are. You know, the smartest people who are doing AI, right? And they come up with a lot of different things, right? And they're still doing that today. So game theory, then learning, of course. So if you have an AI that doesn't learn, it's not an AI, you know. Well, it can still be an AI. That's AI can learn. You can have the ones that learn, the ones that are pre-programmed. We'll talk about that later on. So we have that. An AI needs to be able to learn. It needs to be able to improve itself by looking at more data or getting more instructions. Okay, so the other core goals, natural language processing, which I already talked about, is ability to understand the human language, you know, without the language being encoded in any way, you know, recognizing it, translating it into another language or into another format, retrieving, you know, Q&A, right? So you can now see that NLP was a huge field in those days before the LLMs took over, you know, and transformers came in. But one of the things that you find is that some of the concepts in NLP that were developed are what we are currently using with LLMs. So we'll talk about some of those later. Then perception. Perception is just the ability to perceive something, whether it is vision, in other words, images, pictures, videos, and so on, or whether it's sound, audio, right? Or LiDAR. LiDAR is a special kind of electromagnetic frequency that is used in self-driving cars, right? And then radar is also electromagnetic frequency as well, right? So all of these signals are coming, the AI can interpret it and understand what these things mean, right? Recognize, track it, you know, translate, and so on. Then what we call social affective intelligence, which is basically the AI being able to understand human emotion and being able to simulate it themselves, you know, because an AI being able to recognize human emotion means it will be more friendly to humans, you know. If not, it will likely just behave robotic all through. And then the holy grail, well, not the holy grail, but almost holy grail of AI is what we call general intelligence, the AGI. AGI means artificial general intelligence. So what is artificial general intelligence? It's basically the ability of an AI to solve, you know, any kind of problem. Basically, what makes it general is the fact that the intelligence can be applied in any kind of problem, different kinds of tasks. So even though it is very good in, you know, you train it very well in one area, it can use that training, or it can be trained in other areas and it can become very good in any kind of task. That's AGI. Right now, what we have is what we call ANI. ANI is artificial narrow intelligence. We actually have super intelligent AI in narrow fields. A good example is the chess that I talked about, because right now, the weakest chess engine is better than the strongest human being. The strongest human chess player right now is Magnus Carlsen, who is the world champion. Even though a lot of people are closing in on him recently, but he's still the best, right? But I don't know which chess engine, you know, they basically would just flog Magnus Carlsen with one hand tied, if that is even something, right? Or in chess, what we call piece odds, where you remove one piece, I give you my queen. Actually, Lila Chess Zero will give you one queen and still beat you. Yeah, it beats grandmasters, by the way, without a queen. Something you can check out and confirm. So we already have artificial narrow intelligence, super narrow intelligence. That is intelligence that exceeds human performance, but only in a narrow field. Now, what everybody is looking at is general intelligence, intelligence that can match human performance in everything, right? So that is, but the holy grail is ASI, artificial super intelligence. But that one is, a lot of people are afraid of that because that means intelligence is now smarter than us in every single thing we can think about. And if that happens, That's where we now talk about Matrix. For those of us who have watched the Matrix, where they will now turn us into batteries and be using us to power themselves. By the way, for your information, after you have learned machine learning and how machine learning works, you will know that a lot of those stories are just hype or scaremongering. But there are things that are real though. But there are also things that we should know. You will know what AI is capable of, and you will know what is hype, what is the optimistic. There's this thing we call hype cycle, right? The hype cycle where everybody gets so optimistic about how great something will be. But when they come and see the reality of the capability of a thing, it now descends into what we call the trough of realistic expectation. You now know what the thing is actually capable of. Okay, so that's one way of looking at AI. So in AI, we have the fields of AI. So machine learning is one. So this is now the first difference that you will note between AI and machine learning. Machine learning is a subfield. It's a field under AI. AI covers a lot of other fields of how you can create, machines or software that exhibit intelligence, right? But machine learning is just one of those fields. And machine learning is special in that machine learning focuses on the models or the AI being able to gain its intelligence by learning from the data that you give to it. So you don't actually program it. There are other machine learning fields, which we'll talk about shortly, where you actually program the intelligence into it. Those ones are what we call expert systems or rule-based systems, right? Or fuzzy logic, so many other things. But in machine learning, the code you are writing, you are not programming the intelligence. Rather, you are programming a framework that allows the AI to learn. So this is the difference between AI, one of the differences between AI and machine learning. In some AI subfields, for example, expert systems, you actually code the knowledge, what we call rule-based systems or knowledge-based systems, which are generally categorized under what we call expert systems, right? So that's machine learning. Now, every other thing that has learning in it is also a subfield of machine learning. So you have deep learning, you have natural language processing, you have computer vision, robotics and autonomous systems, expert systems. This slide is not a very good slide. So I'm not going to go through these slides. I'm going to skip them. But these are just different ways people talk about the subfields in AI. But I'm going to land on a slide that will allow me to explain very well. So this is another way that people classify AI, the fields of AI. You still see machine learning there. You see natural language processing. Now, is natural language processing a field per se? Yes, it's a field in the context of what you use AI for. It's one of the things you use AI for, right? Computer vision is one of the things you use AI for. Robotics is one of the things you use AI for, right? So those are applications, areas of applications, right? But machine learning is one of the ways of doing AI. Expert system is one of the ways of doing AI. Neural network is one of the ways of doing AI, but it's under machine learning. Fuzzy logic is one of the ways of doing AI, right? Evolutionary computation, swarm intelligence, cognitive computing. So again, these are considered as fields, but they are not well classified. So you can still see the same thing here: cognitive computing, computer vision, machine learning, neural networks, deep learning, natural language processing. So you see all of these representations or classifications of the fields of AI, they just mix them up and it's not very clear. I actually had a lot of difficulty finding, something that actually does a good job of explaining the relationships, right? This one has tried though, but it's not as good as what I would want. Again, it still puts machine learning as a separate branch, and then it does have deep learning and predictive analysis as subfields under machine learning. They have speech, right? You have speech to text, text to speech, right? It has image recognition, under vision, machine vision, image recognition, right? Machine vision is what you use with robots and self-driving cars and so on. Then NLP, language processing, NLP. So you see how classification, translation, data extraction. Then you have expert system, but expert system is just a way of, achieving AI, planning and optimization, robotics. So at the end of the day, I had to come up with my own chart, and this is my own chart. So this is how I normally classify AI and the fields under AI based on what I have learned over the years, since I started this whole thing some 20-something years ago. So you have AI, artificial intelligence, and then you have two ways you can classify it based on the approach. So you have the first approach, which is symbolic or knowledge-based. So in this symbolic, you want to first of all represent knowledge using symbols, right? And then you manipulate knowledge, right? So that is one category. And under that, you have the logic and knowledge representation, right? You have automated reasoning and planning, you have part and rule-based systems. You have fuzzy soft computing, fuzzy logic and soft computing. You have evolutionary or bio-inspired, AI, like genetic algorithms and, swarm algorithms. So these are all ways of implementing AI, not applications. I'll come to that as a separate classification. Then that's on one side, right? Then on this side, you have statistical and data-driven approaches for AI. Statistical in the sense that you analyze data, you gather the statistics around the data, right? So all of the statistical and data-driven approaches to implementing AI are all classified under machine learning because it basically boils down to learning, right? So in the symbolic, you are focused on how to represent knowledge and how to use that representation of knowledge to manipulate it and achieve reasoning using rules and code. So you actually write code. A good example of symbolic, and I'm going to give this as a kind of task. I'll give everyone the task to build me a game-playing bot using rule-based, symbolic, or knowledge-based. In other words, you will distill your own knowledge of that game and write it as a set of rules. If this, then that. If this, then that. That's symbolic. And if you hear of knowledge-based systems or expert systems, that's basically what those are. It's knowledge-based because it's based on your knowledge. You take your own knowledge, you convert it into some kind of code or set of rules, and you store it. You write the code as a program, whatever programming language you want to use, you write it down. And that's AI. And most people don't know that that's AI. Like if you're actually writing code that says if this, then that, for example, I don't even know what example to use, but we'll come to that. You've written an AI because you have basically written something that can exhibit a bit of intelligence, but it is using your own knowledge of the thing, and you have encoded it and you have pushed it there as a set of rules. Whatever programming language you choose to use, right, doesn't matter, right? Now, the second one is statistical. So the difference is that statistical is not focused on you writing the rules or representing the knowledge. Statistical is focused on you writing a method or a model. You are building a model. So it's when we talk of machine learning, we talk about models. You don't hear of models in symbolic or knowledge-based AI. You hear of models in statistical machine learning, basically, because the model is going to hold the knowledge. But you're not putting the knowledge in the model. Rather, what you are writing, you are building a model in such a way that it can grab knowledge and extract it, squeeze knowledge out of data, not just squeeze it, but accumulate it. So you can give it data in batches. You don't give the data all at once. Or even if you have data all at once, and then later on give it more data, it can adjust its knowledge. So it becomes a model. The model is a representation of what it has learned, right? And then you optimize those models. So the learning It's actually a process of optimization. That is why if you are learning machine learning, you have to understand optimization. And when I say optimization, I'm actually talking of mathematical optimization, maxima and minima. For those who did not do maths, that's where we start looking at the mathematics of it. So when you hear of optimum, the optimum point, if they tell you a quadratic equation, what is the optimal point of a quadratic equation? 2x squared plus x minus 1. Is it positive or negative? You do dy dx, 2x squared plus x minus 1, dy dx is 4x plus 1, right? And so the gradient of that derivative is 4. So it has a maximum point, or the inflection point is 0. So those are all things that we learned, right? So don't worry, we'll do this math. So I want to test people, we'll do this maths. But after that, we'll let PyTorch do all of this for us. But for now, or NumPy, right? But for now, I want people to understand it. So anyway, it is going to be, there's going to be some optimization. You cannot learn without optimization. Basically, the process of training a model is an optimization problem. That's a simple thing, right? So that's why it's very important to understand optimization. And then we have a third set, which I've mentioned here, which is evolutionary or bio-inspired AI. So AI, basically, we always look at, things around us, and we try to see if we can, simulate nature. And being able to simulate nature actually gives us the best outcomes in terms of intelligence. And not just intelligence, almost everything else, because nature is super optimal. Nature is like how many years of being able to optimize different things to come up with the way people look like and the way people behave and all of that, and animals and plants and everything. Okay. So this is how we classify first based on the approach that we are using to implement the AI. So we have symbolic or knowledge-based, and then you have statistical or data-driven or learning models, which is machine learning. Now, let's talk about some of the fields that now fall under the symbolic or knowledge-based AI. Like I said, these are mostly rule-driven, logic-based, or search-based. I just talked about search algorithm that we use for chess engines, right? And a bunch of other games. I can tell you a lot of games. If you have played games, on your phone, computer, whatever it is, chess, checkers, whatever games, there's a very high probability that the intelligence in that game that is playing against you is implemented. There's some kind of search in that intelligence that is playing against you, right? And that's basically because most games are just made up of a tree structure. You start off with a starting position, and then from that starting position, you have several possible legal moves. Then from those several possible legal moves, if you want to draw it as a tree, right? Let's assume, let's take example of tic-tac-toe, right? Tic-tac-toe, or knots and crosses, or whatever you want to call it, right? Where you put X and zeros and X. By the way, that's the assignment I'm going to give to everyone, right? You're going to write me a rule-based algorithm, a rule-based AI that plays tic-tac-toe. And I'm going to basically pit each person's submission against, in a general tic-tac-toe competition. We'll see whose tic-tac-toe is the best tic-tac-toe player, right? So we'll talk about that. But by the way, I did that like how many years ago? I was in 1995. So I did a tic-tac-toe based on that in 1990. I didn't even know I was doing AI then, because I didn't know anything about AI in 1995. But I didn't know how to write code, and I knew. So I just did a game of tic-tac-toe, and I wrote all the rules by myself. Like if the position is this, then this is the move you play. If the position is that, then this is the move. That can work with tic-tac-toe, because the number of moves per position is very small. Maybe possible, tic-tac-toe is a 9x9 grid. So you can even say maximum, that maximum 9 moves, per position. But as you are moving, the number of squares left for you to put reduces. So the number of moves even reduces as the game progresses. But there are some other games like chess or Go or checkers that the number of moves that you can make increases as the game progresses. So it's an explosion of possibilities. That makes it even more complicated. You cannot use rule-based to write a chess engine. It's not possible. So what you can use search, right? So search in this case is go and search all the possible this thing. Then I can now, some positions, I can now say, oh, this position is winning or the other one is losing. Then it will now, the search will now find, and there's something called back propagation. So we'll talk about that. So, but anyway, this is not knowledge based. It's not learning anything. You are the one that wrote all the knowledge into the AI. So the first one, the A that you see here, is what we call the logic and knowledge representation. That's the first kind of rule-based training algorithm, right, that you can come up with. So I want to just make a few annotations here. So typically, for something like that, I want to draw squares. Okay, so this is the first one, right? And this is what we are talking about. So there are four, well, there are different types. This four is just some of a few examples. So we have what we call propositional and first order logic. You have what we call predicate calculus, knowledge graphs, and ontologies. What I just talked about, chess, is a good example of knowledge graphs. Description logics. So that is one, right? The second example that you see is what we call automated reasoning and planning, right? So automated reasoning and planning, some of these things are really old school stuff. Nobody really remembers this kind of stuff anymore, okay? Automated theorem proving, constraint solving, classical planning, search algorithms. So you hear this thing I talked about minimax when I was talking about search or chess, minimax and alpha beta, right? So these are some of the techniques that I use. Then you have what we call game trees and heuristic search, right? Game tree is basically how you represent the entire moves in a game, right? So that's the second category of knowledge-based. Then you have what we call expert and rule-based systems, right? Some of us may have done this. You can see is if-then rule systems, right? If then basically is you saying if this, then do that, right? If the orange is green, then say yes. Some of you may have written chatbots. Have you ever had a situation where, okay, write a chatbot, and then, but you don't have any AI to, run the back end of chatbot for you? Okay, so what do? You go and write your own AI and say, okay, somebody types a question. I would like to go. I've done that before. I think I wrote something like that, a chatbot for a banking app. And the questions, they gave me questions. Say, okay, only these ones. Look for answers. So they gave me the questions and they gave me the answers to them. Like, I want to open an account, or I'm having this problem, I'm having, those kind of stuff. So you now say, if the question is, I want to open an account, or if the question has, I want to open an account, there's a bit of fuzzy logic there as well. Fuzzy logic is like, it's not very clear. So you can take those words, and if it has to do with opening an account, then this is the answer you should give. That's rule-based logic, right? That's rule-based AI. Then we have what we call inference engines. Inference engine is basically an engine that is designed, right, to kind of go forward, make different decisions, and arrive at an inference, and then tell you what the answer is. So they have shells. So you have a bunch of these, okay? Then you have what we call fuzzy logic. So fuzzy logic is logic that is not clearly defined as 0 or 1, right? It's not clearly defined as 0 or 1. So sometimes you have in-between states and so on. So you have what we call fuzzy sets, we have what we call membership functions. Fuzzy, you even have control systems that were built using fuzzy logic, like basically control systems, for those who know about control systems. And then you have what we call neural fuzzy hybrids, which is a hybrid between an artificial neural network and a fuzzy logic control. So you actually see that with all of this, right? Well, in the world of today, nobody really talks about fuzzy logic anymore, except maybe just for historical reasons, like in today's class, or you want to learn about it and so on, because neural networks have basically dominated everything. And then, of course, you have the last one, which is what we call evolutionary based algorithms or methods for implementing AI. Or bio-inspired. So a good example is genetic algorithm. Genetic algorithms are very interesting approaches. So a genetic algorithm, what you do is they actually basically follow the principle of evolution, Mendel's mutation, Darwin's evolution theory. Okay, make some mutations in the code or in the logic or in whatever it is and see how it works. You do that in large scale, large numbers, multiple different mutations on different copies of whatever it is that the model basically that you're trying to improve. So you pit it against whatever the environment is, and then the ones that come out best, you replicate them again, make more mutations and all of that. So it follows that principle. Then you have genetic programming, which is similar to genetic algorithm, but is applied in programming. It's a programming method. Then you have swarm intelligence, which is, think of it like ant colony, where you have single individuals that have tiny intelligence, but when you put all of them together, a lot of them, they can exhibit intelligence that is far more complex and far more capable than each of them individually. So you have the PSO method and the ant colony method. So these are some of the methods that were used in the past. Some of them are still currently being used to implement intelligence. So that's what we call the knowledge base, right? Now, the second one is the machine learning, which is statistical, but we'll talk about that because that's the main core of what we are talking about today, okay? So I'll jump to the last one, which is the other way that we classify AI is normally based on the application, like what is it being used for? So, for example, natural language processing, you can actually use both expert systems or neural networks or any of the classical machine learning approaches, right? So it does not, natural language is not an approach to implementing AI. It's an application of an approach or several approaches. You even find that natural language processing, for example, borrows from so many different approaches to be able to achieve what it does, including even today's NLPs, which have been taken over by neural networks, large language models, and so on. They still use what we call embeddings. Embeddings are principles that came from the old days of feature engineering or knowledge representation. And embedding is basically something that, okay, how do we represent this word, right? It's knowledge representation. So we now have knowledge representation as a piece. Then that embedding is used in a neural network for you to get some of the things that we have. So NLP there means natural language processing. LLM means a large language model. A large language model is basically a model that is very large, that is used for language, processing or interpretation. And when I say large model, okay, so we'll talk about parameters later on when we're talking about neural networks. But a parameter is basically like, think of it as a number of neurons in the neural network. So when they tell you that an LLM has 10 billion parameters, think of it like it has 10 billion neurons. It's not exactly that, because technically most parameters, you need like 3 or 4 parameters to make up one neuron. You need weights and biases. So it's not exactly that. But that's how big these things are. We'll have a better grasp of it when you start training your models and you see how big of a model can you fit into your laptop and train without burning your GPU or your CPU. That will be a very good benchmark for you to know and compare when you're using ChatGPT and Cloud and all the rest of them, right? So then we have ASR. ASR is basically automatic speech recognition. So even before likes of ChatGPT and all these language models, large language models came to the fore, we already had speech recognition and speech translation, speech synthesis. Speech synthesis is you give the computer some words that is typed out and it speaks those words. So it's called speech synthesis or sometimes text to speech. So you see TTS. TTS means text to speech or speech synthesis. Then you have speech recognition or speech to text, STT, speech to text or speech recognition. So these are all applications of AI. Some of them are rule-based, right? And some may be model-based. So some may be combinations of those. Just people have over the years come up with the best ways to combine all of these techniques. Then we have computer vision, which is also a track in this cohort. So image classification, detection of objects in images, detection of motion, detection of edges, and all of that. Scene understanding, 3D vision, translating a 2D flat image into a 3D scene, right? Those are all under computer vision. And it's still application. Old methods are also used. Like there's a library called CV, which if you peep into Daniel's track on computer vision, yes, you do that. You see that there's a library that's used for that. And it's not even based on neural networks, it's based on heuristics, right? But they've added neural networks to it now because it's more powerful, right? It makes it more powerful. So you have both knowledge-based or rule-based plus some heuristics, plus neural networks as well. Robotics and autonomous systems, motion planning. Most of the robots, if you guys have watched Boston Dynamics robots, of all those robots that do backflips and jump up and down and do all kinds of crazy things, those don't really use neural networks because neural networks will be too slow in robot application. This is the one area that neural networks are not yet good enough because of the speed requirement. And this is one of the disadvantages of neural networks. They're not very fast. But they can handle complex problems, complex cognitive or intelligence problems, but they're not very fast. So sometimes you use traditional methods that are much faster because the problems that you're trying to solve are not that much. Balancing, for example, even though pole balancing is one problem that we couldn't solve until neural networks came along, right? So pole balancing problem is a good example. But there are other kinds of things. Robots have to balance. Robots have to plan their movements, what they call route planning or path planning or motion planning, as you can see here, right? They have to plan, when they should start slowing down, because if you break a robot immediately or abruptly, it flips over, right? So you have to plan when you start slowing it down and all kinds of things. So there's a lot of stuff in there. And then reinforcement learning, which is what I talked about, pole balancing and so on. Then we have cognitive architecture. So these basically architectures that are used to, implement some kind of, logic or reasoning and so on. So you now see hybrid symbolic neural systems, basically systems that combine symbolic knowledge-based AI approaches with neural networks that use, machine learning approaches. So before, in the last 10 years, a lot of things have changed. So some of the methods we use today, they did not exist 10 years ago or 20 years ago. And some of the methods that were like the best methods of implementing AI 10 or 20 years ago, nobody's even talking about them today, right? So these are good examples of the ones that were booming in the 80s and 90s, expert system. So everything is programmed. But the thing with expert systems is that when you ask an expert system a question or you give it a task that is outside of the scope of what was programmed into it by the experts. That's why it's called expert systems. The experts that transfer their knowledge into those systems. But if you ask it a question that's outside of that knowledge base, it flops. And that's the downside of expert systems, right? But modern neural networks have what we call generalization that allows them to still come up with something, even though it's outside of the training data, right? So the other one, fuzzy logic control systems were very, very popular in the 80s and 90s in industrial control systems, in oil and gas, in factories, in food processing, and so on, right? And then genetic algorithms were popular in the 90s to 2000, right? People were always talking about genetic algorithms, but again, those have petered out. So you see that each of these things is a cycle when they're at the peak, they're at the height, and then something else overtakes them. So we'll see what happens. Maybe neural networks will be overtaken by something else. I don't know. Then logic-based theorem proving, those were in the 70s when we're trying to really make AI prominent. They were what we call GoFi, good old-fashioned AI, which is in those days basically symbolic AI. But those were not very strong. They were limited in their capabilities. But then that was the beginning of AI, and the knowledge that we have today was still very nascent in those days. People didn't know a lot. But all of these things have basically resulted in the knowledge that we have today about AI. Then what we call case-based reasoning, which is a variant of rule-based reasoning. Rule-based reasoning is you give it rules. Case-based reasoning is you give it cases. The definitions of rule and cases are just, these days, those things don't even really matter. They have constraint satisfaction as the main paradigm. So all of that is AI. Now, what is machine learning? So it has already become clear that machine learning is a branch of AI where you focus on building the model. The model is where the knowledge will be stored, but you are not the one that's storing the model. Rather, you give the model data and you write the code in such a way that the model learns from the data and becomes more and more knowledgeable as you give it more and more data. Simple. So you're not writing the logic for it, but you are building it so that it can learn. And some of the key properties of machine learning. Oh, by the way, this is another definition in Wikipedia. This is a more academic definition. Machine learning is a field of study in artificial intelligence concerned with the development and study of statistical algorithms that can learn from data and generalize to unseen data and thus perform tasks without explicit instructions. So the most important thing is that, one, it learns from data where you give examples of past experiences. Two, it improves over time because you are giving more data. Three, you don't code any rules. It learns by itself. And four, the most important thing is you can use the prediction, classification, and decision making. Because it has seen data, it knows how the data looks like. So what is this data you are using to train machine learning models? First of all, it's normally in the form of, these are the situation. If you are in this situation, or in the past when we were in this situation, this was the outcome. Or when we're in this other situation, this was the outcome. So you give it multiple sets of situations and you give it corresponding multiple sets of outcomes. It learns from the situations what kind of outcome will come up in a particular situation. Now, the benefit of it is that if you give it a situation that is slightly different from any of the ones it has seen properly, it actually does what we call an extrapolation or an interpolation. So for those of us who did a bit of graphs, plotting graphs in maths, there's something we call interpolation and something called extrapolation. A neural network, okay, let me not zero into neural networks yet, but generally machine learning models are able to do interpolation. Each of those examples you are giving is a single data point. So think of it like you have a graph, XY graph, and then you plot 3 points, and you tell it to draw a straight line or a line, a line between those 3 points. In drawing the line between those 3 points, you have created an interpolation between those 3 points. It means that I can pick any point on that line I draw, and that is my prediction. That is my prediction, right? And I'm going to go into that next week in detail when we talk about regression and classification, right? Once you have drawn a line of best fit, that is already what? You have drawn a regression line. That line is called a regression line for those who remember the maths of it, right? With that line, you can now say, if Y is now a different value and X is a different value that you have never seen in your data set, you look at the line and you predict, or if X is this, you predict Y. That is what it is. And that's basically what machine learning does. It's just that instead of using only X and Y, a two-dimensional plane, you're using a multi-dimensional plane. Multi-dimensional plane that allows you to look at not just X, but X0, X1, X2, X3, all the way to X infinity. Well, not infinity, because you are limited by the size of the RAM and the size of your CPU. But X to X something, right? And then you have one Y or a set of Ys that come out from that. And you train the model, and then if you give a different set of X's, it will give you a Y. So with that, you can do prediction. With that, you can do classification. The difference between prediction and classification, well, classification is still prediction, right? There are two kinds of prediction. You have what we call a regression prediction and a classification prediction. A regression prediction, which we'll talk about soon, is a prediction where you are predicting an exact value. So for example, something like if in the last 10 years, the cost of of property in I don't know, Abuja was so and so, and you look at all the conditions that contribute to cost of property, then what will be the cost of property next year based on so and so conditions? You have to predict an exact number or a number, right? That's regression. That's predicting. That's regression. You have to come up with a number. But classification is not coming up with a number, but a class where it should be. So for example, something like if you let me, what can I use? If you, I don't have a good example, but a classification problem would be something like, okay, if you take, let's say flowers or plants, if you take a flower of this color and you have it with another flower of this color and they cross-pollinate, what will be the color of the resulting flower, the flower from the resulting plant? And you can try different colors, right? And then you come up with different. So the classification will be in colors, right? You say yellow, blue, green, even though all of them, the ones we call yellow may not all be exactly the same color, but they fall into a group that we can call yellow. They're all yellowish, right? All greenish and so on. That's now classification, because your answer, you are putting it into classes, basically, or groupings or categories. Then the third thing is decision making. So decision making is, I need to choose between this or that. I have 5 different options before me. Decision making is a classical problem when it comes to game playing. Game playing, you have 5 different moves. Okay, which one should I move? That's decision making, right? The other thing is, well, that's the best example. So to differentiate, this last thing is saying that in traditional programming, right? If I ask you, write a spam detector, traditional programming, you will write a set of rules. It's still AI, right? But it is rule-based or knowledge-based. You are the one that has knowledge of what looks like and like a spam email, right? So you say, okay, if the person says free money, or if the email contains free money, then that's likely a spam. So you just write your code that says, if email contains free money, mark as spam, right? But there will be some, maybe one day your auntie, your rich auntie wants to send you free money. That thing will mark it as spam as well, right? Or another one that is still spam, okay? But it is not, they didn't write free money in it. Your spam detector will not catch it. So that's traditional. But with machine learning, you don't write code that says if the email contains free money, right? With machine learning, rather, you write code that says, okay, show me examples of spam, any email that is spam, and email that are not spam. By the way, when you are training, you have to have 2 types of data, right? You have the positive example and the negative example. If you only give one type of example, like you only give it spam email, it will never learn how to and that's the mistake a lot of people do. They don't realize that. If you give it only spam email, you didn't give it non-spam email. So how will it know? It will just, anything you give it, you say spam. But you have to give it enough spam email and tell it these ones are spam. Oh. And give it enough non-spam email, and then this one is not spam. It eventually learns to differentiate between the two. And then learning those patterns, you can now give it a spam email and say this one is spam. So that's the difference between traditional programming or rule-based and machine learning. So this is the final overview, right? When you look at machine learning, there are three ways you can classify machine learning. One is the training method or the learning method, okay? The training method, so we talk about supervised learning. So in supervised learning, you give it the data and you label the data. So just like I talked about the spam, you give it the data, so you give it the emails that are spam, and you also label those ones, say this one is spam, and this one is not spam. The other one is spam, the other one is not spam. So you have to give it that information, and it from it. That's supervised learning. Also, thing is you don't give it, you give it the data, you don't give it any labels. So you give it a whole bunch of emails and you ask it to figure out patterns in the emails and tell you which one is spam and which one is not spam. That's unsupervised learning. Now, in some situations that works because the question you'll be asking me, how would the thing know that which one is spam? Or you didn't tell it now, but it can see the patterns. So it can actually group based on the patterns it sees. It is now you that will go and see if those patterns make sense or not. Then we have the third approach, which we call semi-supervised learning or self-supervised learning, which is you mix a little bit of the two. You give it labeled data and you also give it unlabeled data. Now, the reason why people prefer unsupervised learning is because it's very difficult to label data. So imagine like if I want to train a spam detector, I would probably need like 10 million emails, sample emails. So imagine, and that's why a lot of guys actually got, they are earning well as, data, what do you call it now? Data cleaning or data labeling or data prepping for machine learning. Because if you're doing manual prepping, so imagine you labeling 10 million emails, right? They send it to you. Okay, go through this. Is this spam? Yeah, you mark it. The other one, by the way, for your information, some of the captcha that we get to use, when we go to some of these websites, some of those data are used for if you are inadvertently labeling data for someone anyway, but that's by the way. So that's the main difficulty with supervised learning is if the data is a lot, it's difficult to label. So I would prefer to do unsupervised and just throw the data at them, right? But instead, what you could do is you can label a few, right? The benefit of labeling a few is that now the amount of work you have to do is much less, but those few that you have labeled gives the model an idea of which features look like spam and which features don't look like spam, right? And then the rest of it that you didn't label, it can then use clustering methodologies to classify and group them together. So all the ones that look like those ones that you label as spam will all come together and so on and so forth. So that is a very effective way. Then we have what we call reinforcement learning. So in reinforcement learning, you're not even giving it any data. You're not saying this is email spam or this is spam email, this is not spam email. In reinforcement learning, what you are doing is you give it opportunities to interact with an environment and then you give it reward. The reward can be positive or negative. So think of it in the context, if we use that same analogy of spam, you have a situation where the agent, you throw it into a bunch of emails. If it clicks and opens a spam email, you pinch it. But if it clicks and opens a non-spam email, you give it some positive reward. That can also be programmed in. And then it begins to learn to know when the pinching gets too much, it begins to learn to know which one is resulting in it getting pinched and so on and so forth. So that's reinforcement learning. So that's one way of classifying machine learning. The other way of classifying machine learning is by looking at the method or the approach of the models. How is the model built, or what's the architecture of the model? What's the technique? So neural networks are like the biggest thing in the world today, right? Because they're based on that principle of neural networks. But you have other models, other methods of building these models. So you have probabilistic model, which uses a Bayesian probability or Bayesian principle, right? Then you also have tree-based methods, random forest, XGBoost. We are going to do some tasks on these ones, right? The random forest, XGBoost, and a bit of the Bayesian probability models before we go into neural networks. Then we have kernel methods, the support vector machine. Then you have graph-based learning, evolutionary or genetic algorithms. So that's the second way you can classify. The third one is you can classify machine learning based on the task that the model does. So like I say, you have classification. So classification is basically you want to classify stuff into different buckets. So you give it data that has been labeled and you ask it to label other ones in a similar manner. Regression is predicting a numeric value, like I said. So regression, you always predict an exact value. In classification, you predict a category or a class. Then you have clustering. Clustering is unsupervised learning, which is basically you want to group stuff that are similar into, they look the same to the AI, right? Then you have anomaly detection, which is where you detect anomalies. Basically, this thing looks different from everything else. Anomaly detection is really good for fraud detection because fraud activities would be somewhat different from normal activity, or virus attacks, or other kinds of cyber security attacks, intrusion, and so on. Anomaly detection is used a lot in intrusion, in cybersecurity, and so on. Then you have what we call recommendation, where you suggest. In fact, that's what we see every day these days, right? You go to Amazon. It's Amazon that actually started it. They recommend that, okay, people that bought this thing also bought these other kinds of things, so that they know those ones will appeal to you because for some reason they have looked at your previous records or history and they match it similar to what other people that have similar history have been purchasing. So they give you those recommendations. Now that's everywhere. People that, if you go to Netflix now, people that watch this movie also watch these other ones, that kind of thing. Or even on the App Store, people that downloaded this app also downloaded this other similar app. Some of them are not actually even machine learning based. Some of them are rule based too, for your information. People just like coded the thing. But a bunch of them use machine learning. But in both cases, they're both AI. Remember, if you do rule based, it's still AI. Okay, that's what most people did not know. Then we have dimensionality reduction, right? Which is basically a way of reducing dimensions. We can talk about that later on. So I'm going to run through this. I'm almost done with my slides. So concepts and definitions, we already know what AI is. It's science of building machines that can perform tasks. An agent is an entity that perceives its environment and takes actions to achieve goals. So you hear of agents a lot in reinforcement learning because in reinforcement learning, the agent moves around in a constrained environment, right? And takes actions. And as it's taking actions, it's getting some rewards. And the rewards that it's getting, right, determine whether I should take that action again next time or not. That's basically how reinforcement learning works. Rationality is, one of the properties or the expectations of an AI that you should be able to choose actions to maximize expected success or utilities. Remember what I said, utility is your outcome. The outcome for the AI is the outcome from taking a specific action or specific sets of actions that lead to a particular outcome. Symbolic AI is AI based on logic rules and declarative knowledge rather than learning from data. So the knowledge is represented using symbols, and logic and reasoning is achieved by manipulating those symbols. The knowledge representation is, yes, how do you encode this knowledge into the symbols or into some other form? Because even in neural networks, for example, or other AI ML approaches, you still need to represent data. So we can talk about that. Inference is when you derive the new outcome from new data, right, based on an existing model. Machine learning is how you teach computers to learn patterns from data instead of explicitly programming them. Training data is the data that you use to train a model in machine learning. And you have to label the output. Supervised learning is when you use labeled examples to train your model. Unsupervised learning is when you allow the model to find patterns in its data, in the data by itself. You don't give it any labels. Reinforcement learning is learning by trial and error, where you give rewards when it does what you want, and you give it negative rewards or penalties when it does the opposite of what you want. Generalization is when a model is able to predict based on information or data it has never seen before, right? So I'll now go into this, which talks about what is it? So if somebody asks you now, what's the difference between AI and ML? I think you know that now. But what's the difference between machine learning and deep learning? So there may still be a bunch of people who may struggle with that. But deep learning is machine learning that uses deep neural networks. So you can see that we are now zeroing into neural networks. We started off with AI, which is a broader approach, the entire field of study of creating intelligent artificial intelligences, right? If I may use it that way. Then AI has different, fields. One of the fields is machine learning, ML. Now, ML uses the approach of training the models. You build a model and it learns from data. Then in machine learning, there are different ways that you implement the models. So we talked about some of them. For example, random trees, random forests, tree-based mechanisms, Bayesian probabilistic models, right? Kernels, support vector machines, and a whole bunch of other things, right? So those are different ways, but there's also neural networks. So when you use neural networks to implement your model, then you are now doing what we call deep learning. But just using neural networks is not enough. The networks have to be deep. So what do you mean by deep? It has many layers. What's the difference between, a deep neural network and just a shallow neural network? Is the amount of computational, that capability that you need. But there's also techniques that you use when you're stacking so many neural network layers to make sure that you don't have what we call vanishing or exploding gradients problem. That's a big problem in training models. The gradient, which is what determines how the model learns, can vanish or it can explode. We'll talk about that later on down the line. So that's deep neural network. So deep learning is a subfield again under machine learning, just like you have all this other learning, right? And then reinforcement learning is just a type of machine learning based on reward, which we've talked about already. So it's good to take note of that. Okay. So I'll just round up by giving us a quick history of AI. So I have a timeline at the end, but these are some of the key milestones, right? Remember I said the field of AI, somebody coined that thing, artificial intelligence, in 1956. That person is John McCarthy. John McCarthy. There was a workshop in Dartmouth, right? And that's cited as the founding event. So in that workshop, this term of artificial intelligence was coined, right? And but before then, you had a lot of mathematicians, philosophers who studied formal reasoning and tried to kind of distill reasoning into representable entities or formats, right? Logic as well, computation. So all of that laid the groundwork. So that's why we say it's not really in that 1956 I started. The foundation started much earlier, right? So machines that think, basically, people always wanted to have machines that could think. In 1943, Warren McCulloch and Walter Pitts, they proposed a model of artificial neurons. We're going to look at that. This is the basis because they basically followed neuroscience, how the neurons in the brain work. So they came up with that. But the artificial neurons were not very useful because for you to get the current level of utility that we're getting out of neural networks, they needed to be very powerful computational capacity or capability of computers. In those days, the computers were just starting, they were not very powerful. So neural networks were almost useless. And that's why they had to resort to these other methods using knowledge base, using a rule base, using symbolic and all of that. In 1950, Alan Turing published Computing Machinery and Intelligence. So I'm sure some of you may have heard of the Turing test. The Turing test is a kind of test that proves whether something is intelligent or not. It's just a test of intelligence without you seeing the thing that is doing the test. So early programs emerged. Immediately they started talking of AI, and that hype started up again. So you had checkers, you have chess, theorem provers, and so on. So chess has been there for a while, but a lot of these chess engines were not as good as, they were not even good enough to beat a human being or play a human being. So there was a lot of different cycles, like I said, success and optimism, then followed by winter, when the expectations were so high, the expectations were not met, and everybody just got disappointed, and everybody withdrew and decided to invest in other things. So the first cycle happened between 1956 and 1974. There was a lot of optimism, right? That's when symbolic AI, rule-based systems, logic programming, the early neural networks that people had a lot of hope on, were developed from 1958 to 1974. Research was at a high momentum. A lot of people were having ambitions that machines will match human level intelligence within 20 years, but that didn't happen. So by 1980, by the 70s to 80s, 20 years had passed, and machines were still falling, way behind. So that was when there was a bit of disappointment, disillusionment, and the limitations of the early approaches were very evident. They were good, but they were struggling with complex reasoning tasks. Neural networks were able to do reasoning tasks, but they were too slow, right? And we were having single layer perceptrons, which couldn't do much. In fact, if you study this thing, you see there's something called an XOR problem. A neural network couldn't solve an XOR problem. We are going to look at that. I will ask you to build me a simple neural network. When we go to neural networks, I will solve an XOR problem. But it couldn't. I actually tried this myself, and I failed. I trained the neural XOR problem. It couldn't solve it. All of this led to a lot of disappointment. So people basically, this Light Hill was a report in the UK that they said AI is not going anywhere. Let's not waste our time and our money on it. So that was the first AI winter, withdrawal of funding and everything, and people just lost interest. But at some point, don't worry, I'll solve it this time. I'll show you how to solve it. So at some point in the future, after the 80s, sometime around the 80s, a lot of new interesting guys kind of came up with new ideas, So instead of using symbolic logic, which was not really good, they started what we now call expert systems, rule-based systems. So they distill their own knowledge into databases, into knowledge bases that had some kind of search algorithms, search trees, and so on. And those actually started solving a lot of problems. So they became popular, and the hype came up again. Governments, industry started investing heavily again. There was a lot of interest. Part of that investment also went to neural networks. So neural networks started again. People came up with this backpropagation algorithm in 1986. Backpropagation is very, very important in neural networks because that's what leads to neural networks learning. A perceptron without backpropagation does not learn anything because backpropagation is what updates the weights, and the knowledge is stored in the weights. So when this came up, there was a lot of hype, interest, and so on. Reinforcement learning and theory matured again. This was again in the 1980s, from 80 to 1990. But again, as usual, so much overhyping of it, so much investment with so much excess expectations. Again, these things did not meet up the expectations. A lot of commercial failures because of the over expectations. And again, reduced funding. People just said, man, remember, this is now a new generation. Or the first generation tried, and so the new generation have forgotten what the old generation, their their disappointment, and they let's try new ways and all of that. And the interesting thing is that a lot of new different approaches came up as a result of that. So at the end of the day, anyway, it didn't meet up those expectations. So again, a second AI winter happened again in the 90s. I remember that very well because I read about it a lot. And then in the 90s, it was like, man, what's going on now? I'm not even hearing anything about AI again. In the 90s, there was nothing like AI neural networks. But other people still continue with different new approaches. It fragmented into much narrower subfields, focusing on narrow intelligence. Let's just prove that AI can be good in this thing. It doesn't have to be good in everything, just good in this thing. That's where you talk about chess. That's where Deep Blue comes in and beats Kasparov and all of that. But these were narrow. Chess was always there, right, in terms of developments in AI. So but sometime in the 90s and thereafter, you start seeing big data. You start hearing people talking about big data. So you now have large data sets. You now have faster hardware. You now have what we call GPU, the graphics processing unit. This is the thing that changed neural networks and therefore changed machine learning and AI. Because with GPUs, you could do inference at hundreds to 1,000 times faster than a CPU, right? And that's where people like NVIDIA came up. In those days, I used to hear of AMD, what do you call him? I can't remember their names again. I can't remember, but there were a bunch of people that manufactured GPUs in those days. So GPUs came and turned things around. You could train models faster, but it's still not fast enough. We had larger data sets. This was all because of the internet, because the internet came in the 90s, right? From 2000, the internet came in, a lot of people, a lot of interaction, social media, so many things that came up, a lot of data came in, and GPUs came, it's almost like everything came in at about the same time, newer methods, faster hardware, GPUs, improved algorithms, right? And large data sets. And we started a boom again. And that's a boom that is still continuing till today because people started building stuff. AlexNet was built in 2012, which is a deep neural network that achieved a major breakthrough in image recognition. Before, we used to use heuristics for image recognition, handwriting recognition and all of that. But neural networks started picking up. And after that, we now have the transformer architecture. Before then, we had stuff we call CNNs, convolutional neural networks, that were used for image recognition. They were really good. They changed a lot, but they were not that good. But somebody came up in Google, by the way. A lot of these guys are researchers from Google and some of the big, companies. And they came up with this very seminal paper called Attention is All You Need. We used to talk about attention before then. By the way, this happened after I had even, I studied all of this in 2016, where I studied about CNNs and all of that. And I did not even know about the transformer paper in 2017. But that changed a lot, right? And from transformers, we had better recurrent neural networks that could learn. You could train them much faster, more parallelized training with all the GPUs and all of that. And everything blew up. By 2018, transformers were everywhere. By 2019, by 2020, OpenAI started also thereabouts. I don't even have all of that, but you can check in this slide. On the right-hand side, you see some of the key milestones, right? 2016, yes, AlphaGo defeats the world champion in Go, right? And this did not use transformers. This used convolutional neural networks or residual networks. And then in 2017, transformers came up. In 2018, AlphaZero again. And then from there, 2019, by 2020, we had OpenAI or thereabouts. OpenAI started up, and that was it. By 2022, we had what we now call ChatGPT, what we call generative adversarial networks, right? Pre-trained models, transformers, generative pre-trained transformer. That's what GPT means. The best of all the methodologies for neural networks. And once ChatGPT came up, everything blew open, and that's the story we are living in now. So consider yourself very fortunate. You are in an era where AI is booming. And we are hoping that this time around, right, we will not have another winter. But just in case we have winter, prepare your winter coats so that when the winter comes, at least you will still be warm. Okay? Learn your skills. This is the time of AI boom, and you are very well placed. So I really needed to do this history. I'm not going to spend this much time talking again. From here on, it is coding, coding, coding. But I hope you enjoyed this session, and I hope you picked up a few things from this history lesson. Thank you, and thank you. So I think I'll pause, I'll end the recording at this point, and we can have the questions after now.
Thank you.